Welcome back. In this class, we'll be looking at how to measure the performance of queuing system, or how to measure the queuing performance, or queue performance, or queuing models performance. Now here, we'll take a look at several parameters that we use to evaluate the performance of queuing models or queuing system. The first one is rho, and it denotes the utilization factor. It could also be referred to as the probability of all servers being busy. Probability that all servers in the system are currently being busy. The next one is LQ. It represents the average number in the queue. The average number in the queue. For instance, in the hospital example that we made reference to earlier, the area, the waiting area or the queuing area, the number of customers that are there represents LQ. That is the average number in the queue. All right. Then L represents the average number in the system. That is both the ones on the queue and the ones being served. All of them together represent L. Then we also have WQ, average waiting time in the queue. That is the time customers spend waiting on the queue. And then WQ represent the W represent the average time in the system. That is the time that customers wait on the queue and the time that they spend being served altogether. Then P naught is the probability of no customer in the system. Pn is the probability of exactly n customers in the system. Then finally, Pt is the probability that the service time will be greater than time t, denoted by Pt is equal to the exponential of the negative of the service rate multiplied by t. Now, having looked at the parameters for evaluating the performance of a queuing system, we want to look at Kendall-List notation, or simply Kendall's notation. The notation for describing the characteristics of queuing model was first suggested by David G. Kendall in 1953. Kendall's notation introduced an ABC queuing notation that can be found in all standard modern works on queuing theory. All right, we represent that as A/B/S/M/N, where A represents the arrival distribution. All right, and we have said earlier that the arrival could be essentially follows Poisson distribution. The arrival could also be deterministic. It could also be a general distribution. Then the service time distribution could be exponential, usually exponential, but it could be deterministic and it could be general distribution. The service, the C represented by S denotes the number of servers, the number of what? Servers. Then we have the M and N that usually we do not bother about in most representation, because we assume that they are infinite queue capacity and infinite population. They represent infinite queuing capacity and infinite population. So we usually ignore them, since they are usually assumed to be infinite. But in the case of finite, we'll have to represent the M and the N with the appropriate capacity. Now, there are assumptions that we make in the queuing models. For the queuing model that we discuss in this class, we'd have the following assumptions. One, we assume that arrivals follow the Poisson distribution, like we said earlier, and the entities will get served on a first in, first out basis. All right. The another assumption is that it is a single phase. The entities gets up on a single phase. Do not mistake single server and single phase. When we're talking about phase, we are talking about something like stage. They only get served at one point and what they depart. That is the kind of assumption that we make in the course of this class here. Then the fifth one is that, sorry, the fourth one is unlimited queue length. That is infinite queue length. We do not assume that there's a restriction to the queuing length of the model that we discussed here. And we also assume that all of these things take place at steady state condition. All right. Then the five most commonly used queuing system are presented here. They are presented here. Sorry, let me expand this a little bit so that you can be able to visualize all of it. Okay. Let me reduce this little. Okay. I think you can see clearly here. So the five most commonly used queuing systems are presented here. The first one is the simple system, which denoted by MM1. We use Kendall's notation to represent their name here. MM1 system, that is customer service desk is in a store. That is an example of MM1. We have just one server, that is one checkout point. In the case of the supermarket example we gave earlier. So we could also have multiple servers represented by MMS, that is the service follows an Poisson distribution, and the arrival follows Poisson distribution, the service follows exponential distribution, and the queuing system has a multiple server here with server greater than one. An example is the airline ticket counter. When you get it, you have more than one person that are attending to customers when they arrive. Another one is the constant service, denoted by MD1. That is, the arrival follows Poisson distribution. However, the service follows a deterministic distribution, all right? That is, the service time is constant. Service is constant. However, it is a single server. This is an example. For example, we have an automated car wash. This is an automated car wash, all right? It's an example of the constant service queuing model. Then we also have the general service denoted by MG1, a single server. An example is the auto repair shop. And lastly, we have the kind of model with limited population. Like we said earlier, you can see that instead of having nothing here, N here represents the population, the capacity of the calling population. There is a restriction here, such as the case of a textile company that we made mention of that contains 30 machines. All right, so this has a limited population. However, the queuing capacity is infinite, it's unlimited. So an example is an operation with only 12 machines that might break. All right, in this case, we just have 12 machines in that company that might break down. That is to say that the population is what? 12. The calling population is what? 12. So we look at the next thing here, Little formula. Little formula. Let me position this again so that we may look at it like this. Okay. Now, Little's formula. In many queues, it is useful to determine various waiting time and queue size for particular components of the system in order to make judgments about how the system should be run. All right. In doing this, let's assume that the average number of customers in the queue at a given time is represented by L. assuming that it's a steady state condition. Let's also assume that LQ represents the average number of customers waiting in the queue, and let LS the average number of customers in service, that is the number of customers that are being served. Now, since customers in the system can only either be on the queue or being in service, we can write that L, which is the average number of customers in the system, we can see the average number of customers in the system is equal to the average number of customers in the queuing area, all right, plus the average number of customers being served. That is L equals to LQ plus LS. In the same way, we can say that we assume W to be the average time a customer spends in the queuing system. All right, and WQ is the average number of time spent in the queue itself. All right, the average time the customer spent waiting in the queue before being served. Represent that as WQ, and we also represent use WS to represent the average amount of time customers spend at the service. Okay, we can then write that W is equal to WQ plus WS, that the total waiting time in the queuing system is equal to the time that customers spend waiting on the queue plus the time customers spend being served. You should remember that all of these parameters are assumed to take place at the steady state condition. All right. Defining lambda as the arrival rate into the system, that is the number of customers arriving the system per unit time, it can be shown that L, which is the total number of customers in the system, can be derived as the product of the arrival rate and the total time a customer spent in the system, W, that is L equals to lambda W. Now, it could also be shown that LQ, which is the total number of customers waiting on the queue, can be derived as the product of the arrival rate multiplied by the total time customers spend waiting on the queue. That is LQ equals to lambda WQ. In the same way, it has also been shown that LS is equal to lambda WS. This is known as Lithiu's formula. It is known as Lithiu formula. Now, in our next video, we will continue from here. I hope you enjoy this class. Thank you for listening.